I think I better go check my office. See if he's called. He has my cell phone, right? I did miss a call from somebody. Is that William? Hello, hello. I'm checking my messages. Not there. Where did I put? Not there. Could be in my box. Roseburg. Hello, is this William? Hey, it's Gary. Did you get my invite? Okay. I sent it to your Gmail. Bummer. Let's see if I can figure out how to send it again. So unless I got your address wrong, let's take a look here. Let's see, WLLMHLMN123. Sounds right. I just copied and pasted it in. Let's try sending it to your college accounts. And you can get the link and try and log in with the Gmail accounts. Let's see. Okay, so I'm also inviting you through your college account. There it goes. Should get to you momentarily. Any luck there yet? Do this. Try sending me a message from your Gmail account, just in case something went wrong with the typing, copying, and pasting of that address. You got an invitation? Okay. So that should take you to the Hangout, and then from there you should be able to sign into the Hangout with your Gmail account, I think. Okay, I don't see you here yet. Hopefully it'll appear momentarily. Oh, there you are. Series on the screen. I hear you too. You have a microphone there?
Yeah.
Okay, so I'm going to hang up the phone now since we've got this going. Okay, so let's see. How do I make this just so you can see my screen fine?
Yeah.
Okay, good. So as of, let's see, yesterday I have recordings and notes in the doc sharing section up through section 1010.
Okay.
So you're a little bit behind on your homework. What
Yeah.
can I do to help you out?
Oh, well, all last weekend I was studying for my AP test, but
Oh, right, yeah, you told me that, so you have some work to do. So
yeah.
I told everybody else that they can have a week from now to get ready to take the test on the remainder of chapter 10. So that's 10.7 starts power series, and then we did 10.8,
Okay.
10.9, and 10.10. And 10.10 is essentially just a review. It's one extra technique for power series, but mostly it's just a review of the other stuff we did in power series.
Okay.
So let's see, and I'm going to post today two practice tests to get ready for it. One paper one like you're going to get, and then another I'll do kind of like the homework with the computer system.
All right.
So do you have some specific questions about power series, or do you want me to just kind of give you an overview?
That would be good. I think I'll get caught up and we can reschedule a meeting for some time.
Okay.
And then I'll ask questions that I have.
Okay. And then most evenings and weekends I'm free to schedule something too,
Okay.
if you wish. So just let me know. All right. So the idea of power series comes from geometric series. So the simplest geometric series I could write would be 1 plus r squared plus r cubed, and that just keeps on going.
Okay.
And in summation notation, I would say that's the sum as n goes from 0 to infinity of r to the power n. And when we first did geometric series way back in the beginning of chapter 10, like 10.2 I think it was, we discovered that as long as r was a proper fraction, positive or negative, right?
Yeah.
So that means r could be less than 1 or greater than negative 1, then this will converge.
Yeah.
So if that's true, there's a lot of different r values I can plug in, then really I can say this is a function. And that function is just an infinitely long polynomial. So I'm just going to replace r with x.
Mm-hmm.
And so on. And we were also able to prove that this thing converged. The geometric series converges to the first term is in the numerator, and then 1 minus the base is in the denominator. And so that's going to be true here. On the interval from 1 to -1,
Mm-hmm.
this infinitely long polynomial will actually converge to the function 1 over 1 minus x.
Okay.
So this opens up a whole new area of mathematics. So instead of just looking at a list of numbers like 1 plus 1/2 plus 1/2 squared, I have a function that's represented by an infinitely long polynomial. And so these infinitely long polynomials are called power series.
Okay.
And at this point, we have 4 ways to create power series. Oops. So based on that geometric series, we can use substitutions to change the way it looks.
Mm-hmm.
If the power series has a convergent interval, then we can differentiate an infinitely long polynomial. Alternatively, we can integrate to get a new one. And then 4, we can create what are called Taylor series, where we use repeated derivatives to discover what the coefficients are.
Okay.
And Taylor series has been what most of this has been about. So section 10.7 covers the substitutions, differentiation, integration, and then 10.8, 9, and so this is all 10.7. And Taylor series are essentially 10.8, 9, and 10. There's a fifth method that's not as useful as the others, but I'll mention it now anyway, because I did go over it yesterday in class, and that's called the binomial series. But I'm not going to talk about that one right now. You can look at the video later for that one.
Okay.
It's pretty cool. It allows us to find some series pretty easily and describe the coefficients, but it only applies to a select group of functions. So I'm going to do the, I think I'll do a substitution integration for you right now.
Okay.
So I know that the function 1 over 1 minus x is on the convergent interval equal to 1 plus x squared plus x cubed and so on. So this is just the basic geometric power series. All right, and there's its summation form. So what I'm going to do now is I'm going to do a substitution. I'm going to substitute negative x squared for x. So everywhere I see an x, I'm going to replace it with a negative x squared. So in my new formula, I'll have 1 over 1 minus parentheses negative x squared. On the other side, I'll have 1 plus parentheses negative x plus parentheses negative x squared and so on. Negative x squared, negative x squared, negative x squared, there we go, cubed, and so on down the line. So then I want to clean this up and see what it looks like. So in the function side, minus a negative, that's really 1 over 1 plus x squared. On the other side, I'm going to have 1 plus negative x squared, which I'll write as minus x squared. In the third term, if I square a negative, it cancels, and x squared squared would be x to the 4th, right?
Yeah.
What's the next term going to be?
Minus x to the sixth.
Correct. It'll be minus x to the sixth. So this is kind of cool. We generated an alternating power series.
Mm-hmm.
So the formula for this one, if I were to write it in summation form, is going to be the sum as n goes from 0 to infinity. I'm going to have a -1 to a power. And then the question is, the power is either n, or it's going to be n minus 1 or plus 1. So we'll have to decide on that. If we start at 0, -1 to the 0 would be positive.
Mm-hmm.
And then if n is 1, -1 to the 1 would be negative. So that works with my sequence, positive, negative, positive, negative.
Okay. Yeah.
So I can erase this or part. All right, and then I'll have, it looks like I have x to the power 2n. Do you agree with that?
Yeah.
Because here is where n, oops, my pen gets a little crazy sometimes. Here is where n is 0, here is n is 1, here n is 2, and so on.
Yeah.
Okay, so it's usually a little bit of work, but sometimes it's not too bad writing it in summation form. Do you have to write it in summation form? Sometimes you do. You write it in summation form when you have to apply a test, like the ratio test.
Mm-hmm.
All right. So the next thing we need to figure out is, what is this convergent on? And generally, when you do substitutions, integration, and differentiation, you inherit an interval of convergence. So we're going to inherit the previous interval, sort of. The previous interval
Was it
was
-1?
absolute value of, or yeah, we could do either way. So Control Z that. All right. So it was that x was between 1 and -1, but I replaced x with a negative x squared.
Mm-hmm.
So in that old interval, I have to put my new substitution in there and solve it.
Yeah.
So here, I would want that negative by the x squared to go away, so I'd multiply all three sides by -1, and that'll switch the inequality too. So that's going to be 1 is greater than x squared, which is greater than -1, which I could just write in the opposite order. -1 is less than x squared, so that doesn't matter. To solve for x, I would then take the square root. And the problem on this left side is the square root of -1 is I, so that is not helpful. So it's only this side that I want. The trick with square roots and inequalities is that the square root of x squared has to be viewed as the absolute value of x.
Yeah.
And that's going to be less than the square root of 1, which is 1 in this case. Which turns out gives me the same interval I had before. So it was just a coincidence that worked out nice like that. So it turns out still x has to be between 1 and -1. What can happen on a substitution or an integration or a differentiation is you might end up with a less than or equal to on either side. So you always check the endpoints next.
Okay.
To see what happened. So in other words, this number right here is what I call the radius of convergence. The radius is maintained when you do a substitution, integration, or differentiation, but the endpoints may change. So that means we have to go back to this right here and plug in 1, see what happens, plug in -1 and see what happens.
Yeah.
Okay, so let's do that. So if x is equal to, let's do -1 first, then I'll have the sum as n goes from 0 to infinity of -1 to the n, parentheses, -1 to the 2n. We have to think about that for a minute. So the 2n means I'm squaring the -1, and if you square -1, you get 1. So that means this is really the same as 1 to the n, which is always 1.
Yeah.
So that means I get the sum as n goes from 0 to infinity of -1 to the n, which would be 1 minus 1 plus 1 minus 1, which we can apply the alternating series test to, or the divergence theorem. And the divergence theorem says, that was like the first thing we learned in chapter 10, section 2.
Yeah.
If the limit as n goes to infinity of your terms an is greater than 0, then you're done. It diverges.
Oh, okay.
And this is going to, ignoring the sign, it's going to 1. So this diverges.
Okay.
By the divergence theorem. And that's one of the tests, part of the alternating series theorem has 3 conditions you have to meet. You remember those?
I don't.
Okay, so the first condition is that it strictly alternates, which is positive, negative, or negative, positive, negative, positive.
Mm-hmm.
This is true. It does strictly alternate. So I can check that off. That's good. The second condition is that the terms don't increase.
Okay.
The algebraic way to say that is a sub n plus 1. The next term has to be less than or equal to the term before it.
Oh, yeah.
And here, they're bouncing up and down. And so I fail this step. Because I can pick a point like right here where I have the next term is 1 and it doesn't meet the less than or equal to the next term, negative 1. So I fail right there. That make sense?
Yeah.
And the third thing, I don't even need to check the third since I failed the second, but the third one is that if you take the limit of your terms, and they call them u sub n's in this part, which means ignore the sign. If that goes to, that's got to go to 0. And these guys are 1 or negative 1. They don't go to 0. So it turns out we fail the third step too. So if you fail any one of those, then it doesn't converge. If you pass all 3, then it does converge.
Okay.
That's the alternating series theorem. Okay, so what have we found? We found on the left endpoint it diverges. So next we check the right endpoint. And sometimes you can just look at it and it's pretty obvious, but not always. So here I have the sum as n goes from 0 to infinity of negative 1 to the n. And I'm plugging in, instead of an x, I'm plugging in 1 to the 2n. And that's the same thing I had before. So based on the previous work, this diverges too.
Okay.
But you got to check each one because you never know what happens.
Yeah.
Okay, so I've made a new power series. My power series is the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n. And it has a radius of convergence of 1 and an interval of convergence not including the endpoints.
Okay.
All right, and so what is that? That's 1 over 1 plus x squared, 1 minus x squared plus x to the, let's see what's next, 0, 1, 2 to the 4th, minus x to the 6th, plus x to the 8th, and so on. All right, next thing we're going to do is we're going to integrate this sucker. So we're going to integrate the left side, and we're going to iterate term by term on the right side. Do you remember the antiderivative for 1 over 1 plus x squared?
Oh, it's one of the inverse.
It is, yeah. Inverse tangent.
Yeah.
I usually refer to it as the arctangent.
Oh, yeah, that.
Yeah, so it's the arctangent of x. So we're about to find a series for the arctangent of x, which is kind of cool. Now, there's an arbitrary constant, and I'm just going to put it on this side. Oh, you got pinball games going on there?
It's the phone, but it's probably just a telemarketer. Sorry.
That's right. So what's the antiderivative of 1?
X.
X. Okay. Minus the antiderivative of x squared.
1/3 x cubed.
Yeah, I'm going to write it as x cubed over 3 if that's all right.
Yeah.
Antiderivative for x to the 4th.
X to the 5th over 5.
Excellent. Right. So now we got a pattern for a new series.
Yeah.
So I don't need to list all of them, but I just list a few to get a feel for it. So I'm just going to go plus dot dot dot. Okay. Next we need to figure out what C is. Now this is going to inherit the radius of convergence, which means x equals 0 is right in the middle. And that turns out to be a super convenient number to plug in.
Mhm.
Do you remember what the arctangent of 0 is?
I don't think so.
It turns out to be 0 if you plug it into a calculator.
Yeah,
On the other side,
makes
I'll
sense.
have c plus, and if I put 0 for everything else, it's just 0. So this tells me that c is 0. So the series, the power series for the arctangent, is that right there.
All right.
Now, here's what's really cool about that. Way back in section 10.4-ish, I think it was, we had the series 1 minus 1/3 plus 1/5 minus 1/7, and so on.
Mm-hmm.
And according to the alternating series theorem, I call that the AST, this thing passes all three conditions and it converges.
Yeah.
The problem is we did not know to what value it converges.
Mm-hmm.
However, that series right there is this series with x equals 1.
Okay.
So if I make the connection between this and x equals 1, then I can say that the arctangent of 1 has to equal 1 minus 1/3 plus 1/5 minus 1/7, and so on down the road. Do you remember what the arctangent of 1 is? So that means the tangent of some angle equals 1. On the unit circle, tangent is slope. What angle goes with a slope of 1?
Oh, it's 45 degrees?
Yeah, so in calculus, we can't use degrees, though. We have to use radians. So
pi over
according
4.
to this series should be pi over 4. So this series gives us a way to approximate pi. One problem with this, though, it grows very slowly, painfully slowly.
Yeah.
So power series give us a couple of different things. They allow us to now find the convergent value for some other series, regular series that we looked at before, but they also open up whole new classes of functions that didn't exist for us before now. So I got one more minute and then I'm going to have to get to my next class. So just an example, here we integrated 1 over 1 plus x squared, and we had no problem saying that that was the arctangent. That was proved back in Calc 2, right?
Yeah.
If I asked you to integrate the sine of x squared, it turns out there is no fundamental antiderivative. So there's no functions you've ever seen before in your life that satisfy this. However, we do have a series for the sine, and we could substitute x squared into it, and then we could integrate that, so we could create a power series for this.
Okay.
Which means now we can evaluate the integral. So in a similar manner to the problem we just did, we can do this problem by creating its power series. All right?
Yeah.
So that is an overview of section 10.7. 10.8, 9, and 10 go over what are called Taylor series. And Taylor series takes the idea of finding a tangent line, and it turns it into the idea of generating tangent polynomials. Is one way to think about it.
Okay.
So my first presentation on Taylor series on YouTube talks about that relationship.
Okay. I'll look.
So check out that and try some of the homework in 8, and then give me a call or email soon, and we'll set up another chat.
Yeah.
To get you caught up.
Thanks.
All right, you're welcome. I got to sign off now.
Okay.
Okay,
Bye.
bye, William.